Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. In this session we're going to look at oblique impacts with a fixed surface. In a direct collision between two objects, as we've already discovered, external forces contribute no impulse. Now the reason for that is that the impulse is considered as taken over a very small period of time with large impulsive interactions between the bodies concerned in the collision. And during a small time, therefore, we'd expect external forces to make little contribution. So we model it by saying that the external forces make no impulse or impact on the system during the collision. The momentum of the system is conserved, though that follows from the previous point, because in effect we're saying that the external forces don't contribute to the system, so if we consider the system as a whole, its momentum must be conserved. Newton's experimental law of restitution holds. That gives us an additional piece of information to build in to the model in order to perform calculations to estimate the outcome of particular collisions. Momentum, I remind you, is the product of mass and velocity, and it's a vector quantity. That vector nature becomes increasingly significant in the developments of oblique collisions. Finally, the experimental law has that form for the impacts we've met so far of balls or objects combining in a line. We'll see how it can be applied in this context too. For the moment, remind ourselves that E is the separation speed divided by the approach speed. The coefficient of restitution is in effect a measure of the nature of the materials, the sort of interactions the materials produce involved in a collision. So let's look at a direct impact with a smooth plane. Now in a direct impact with a smooth plane we have an approach velocity u in a line perpendicular to the plane, and we have a bounce back velocity v still in the same line. Now under those circumstances we know that since the plane is fixed, we can regard its velocity after and before as unchanged and zero. That makes the restitution law very simple. It's essentially v over u, because the separation speed is determined by the object's speed alone if the wall isn't moving. Similarly, the approach speed is just u. So the separation speed over the approach speed in this context gives us the relationship that v is always equal to eu. Now we can't apply conservation of momentum here because the wall is held fixed. When the ball impacts the wall is subject to a high force over a short time, and its rigidity is assured only by assuming that the foundations of the wall exert similar large impulses to keep it firm. They're external forces, so we can't apply conservation of momentum. So we now look at an oblique impact with a smooth plane. The first thing to consider is what's going on in the interaction. If the plane is smooth, it means there's no force in that diagram vertically. No friction at all. That means to say that in terms of interaction there's nothing on which to base it. So the interaction force between the wall and the ball must be perpendicular. And that leads to the fact that the impulse also is perpendicular. Now, as we've just said, you can't apply conservation of momentum because as regards the wall you have an impulse which apparently has no effect. That is not sense. There must be other impulses acting, and they come from the foundations or whatever else is mooring the wall. So no, we can't apply the conservation of momentum, but we do have the benefit that we can apply Newton's law of restitution perpendicular to the wall, and we can say that there is no impulse with a vector component along the wall, so that must mean that the ball's velocity is unchanged in that direction. So the speed parallel to the plane is unchanged at impact, and we can use restitution perpendicular to the plane. Now what that boils down to is that if you draw a picture showing a velocity of approach uw with respect to the axis below, the upper one being the horizontal one, then it changes into minus EU because of the restitution law, and on the other hand the component along the wall is unchanged. Now let's see this in a demonstration. So I'm going to call up GeoGebra. There we've got an approach velocity of 4. The angle is 30 degrees, which is going to lead to 60 degrees between the approach and the plane of the wall. So let's start that. Now you see that the angle is decreased, and the reason for that is that the component in the perpendicular direction is reduced because E is only 0.5. whereas the component in the perpendicular direction is unchanged. If we increase E to 0.1, which would give us a perfectly elastic collision, that's where the bounce back speed is the same as the approach speed. The component perpendicular to the wall is reversed, then you can see that we get a symmetrical situation. Whereas if you take E as 0 at the other extreme, then what's happening there is that the component perpendicular to the wall is being completely absorbed by the wall. But you still have a lot of velocity along the wall because the wall can't change that. There's no friction. So we try another value. U is 3. You're not going to see anything greatly different happening. Let's try 0.6, and we'll, just for a thrill, we'll rerun it. There we are. So each time you've got the question of working out the speed and angle for the bounce back. Right, back to where we were. That's all summarized by this pair of vectors here, that if you have UW for approach, you'll get minus EU and W for the bounce back, for the reflection velocity. So now let's look at a specific case. Let's suppose that we've got a ball coming towards a wall or a particle. We're modelling it as a particle anyway, with a speed of 4 meters per second, with an angle between the approach vector and the wall of 60 degrees. Now what we need to do first is turn that 4 into vector format. So if we take the usual axes like that, then what we need is a triangle with the 4 on it and a 60 degrees. This is not going to look really the best of shapes because that's a long way off 60 degrees, but it will serve the purpose. This is 4 and that's a right angle. Now we can see from that triangle that this side will be 4 sine 60 degrees, and since in a 60 degree setup you remember the triangle for 60 degrees, you have root 3 on this side, 2 on this side and 1 on this side. We can see that sine 60 is root 3 over 2, so that is going to be just 2 root 3. On the other hand, this side gives us 4 cos 60, and cos 60 from that triangle is a half, so that equals 2. So our vector is 2 vertically and 2 root 3 horizontally. We need that in order to apply what we've discussed before. So on the next page, here we have the velocity of approach, the 2 root 3 over 2, and then we're going to put in a new velocity, and the way we calculate those components is that we know that parallel to the wall there's not going to be any change, so the 2 is carried over as V2. On the other hand, perpendicular to the wall, we use the coefficient of restitution, and that will mean that the 2 root 3 is multiplied by half. So there are those two calculations. So we now know what that vector is. Now the question asked us what was the speed and velocity. So now that we've got the velocity vector, we can answer the question. The velocity is minus root 3 over 2 with respect to the axes shown here, and the speed, using the usual Pythagoras calculation, is the hypotenuse of a triangle with sides 2 and root 3. There we are. So you'd expect that to be 3 plus 4, that's root 7, which is 2.6, etc. Now we could also calculate you see we've got the angle alpha shown in the picture. We could also calculate the angle alpha, should we be so interested, even though the question doesn't ask it, and that would come by doing trigonometry on that triangle, that we want the inverse tangent of √3/2. So that wasn't asked, but it's there if we were interested to see by calculation what the animation was showing us. So there's our answer. As given in context with the units, rounded appropriately, that should be a 3, shouldn't it? There's a slip of the pen developed there, but we'll soon put that right. That should be a 3. So that brings us to the end of that presentation. The next one is about the loss of kinetic energy in these oblique impacts.